the area of this parallelogram. I would like to make a third component. So what would be this k component or the z component? 0. Now what's vector b?
That's 5 minus 4, that's 1.
5 minus 4 is 1, right? Oh wait, so we gotta get this point, right? 4 minus the 1, right? We're doing this one?
Oh yeah.
Tip minus tail, right?
minus tail,
Not
okay.
that vector, very good.
4 minus 1 is 3,
Cool.
and 3 minus 2 is 1, and 0.
Let's cross them, get the magnitude, we've got the area. We'll cross the vectors, then we'll take the magnitude, we'll find the area. Alright, well then what is A cross B? Alright, I'm gonna have to do what to this thing?
I did here,
That's
right?
all you do. If you want to write this, you can. They call this the determinant. We're finding the determinant of that matrix. What about the first column? 3 times 0 minus 0 times 1.
0.
Now when I get a 0 there, this is weird. You might be like, what am I going to get an area of 0? Impossible. We can see it has some area. Let's just keep going. How about the middle component?
Middle component 1 times
1 times 0 is 0.
and 0.
Minus 0 times 3, 0. Change the sign.
Negative 0, 0.
Negative 0 is 0. Well, this then has to have a number. Do you agree?
Yep.
It's got area. We can see it. It's not an area of 0. All right, yeah, sure enough. Now we got it. 1 times 1?
Minus.
Minus 3
Nine.
times 3. Negative. Area negative? No, the key is we're going to get the magnitude of that vector. That's going to give us the actual area of the parallelogram. So the area of the parallelogram will be whatever the magnitude, so I'll put the bars, of that vector 0, 0, negative 8. Unless you want to write it like this, everyone. Magnitude of vector negative 8k, if you like to put it in standard basic form. I'll leave it like that. How do we do magnitude? Square root of
64.
0 squared plus 0 squared plus a negative 8 squared. I love you're doing it in your head. What's the square root of 64?
8.
Oh, it's an 8. What's the area of the parallelogram? 8.
But don't you need the sign thing on the area of the parallelogram too?
I love it. It was like he knew that you could do this. You could have done some geometry. See, there's other ways to do the problem. You could have gone in here and found that angle. Do you agree? You go, how can I find that angle? You could have done trigonometry.
Okay.
But I thought, hey, we just had to get the what? Magnitude of the cross product. So there's other ways to do that problem. In fact, you might be like, I can figure out that base right there, and I can just do base times height. Absolutely. But then I just wanted you to see this connection. So there is another way to do the problem. You go, if I can determine that angle, and you go, well, how can I determine that angle? You might go back and do this math. You could find that angle that way, right?
Yeah.
But you'd still deal with vectors. That's why I thought, hey, if we can get the vectors and just cross them, we just need the magnitude, Joe.
In case if you had to find the angle, how would you have done that?
There's a few ways. Because you see in this math, you got this slanted line right here,
Uh-huh.
going to 2, 5, and this slanted line.
So to draw like a H virtual.
I love it, Art, and I love what you're thinking when he's trying to determine this angle and he's using geometry. But this is the beauty of vectors now. The beauty of vectors, man, it just opens up a whole new world of mathematics, makes it easier to determine what? Angles, through these two formulas. So the whole idea is this is the way to go. You go, I'll create vectors from points. All you have to do is create vectors from points and you can get a what? You can get an angle that way, right?
Okay.
But I think you would have found yourself, you would have done that, but you still would have had to get these vectors, wouldn't you?
Uh-huh.
So you could have, we were able to avoid getting that angle.
Angle.
But do you agree, you can now figure that angle out right now by either one of those formulas.
Uh-huh.
If anybody wants to know that angle right there, you absolutely can find it out right now. Because we know this, we know that, and we know that, don't we?
Okay, got it. Yeah. The sign inverse.
That's right.
Okay.
Be inverse sine of that. Did anybody want to find the angle? I don't either. But you could. It would be quick. Be quick math. Really, yeah.
So the
They
cross.
didn't ask us to do it.
So the cross product divided by the magnitude.
That's right.
Okay.
The cross product
Divided by the magnitude.
of the two would be the magnitude of those two vectors.
Gotcha.
Excuse me. The magnitude of the cross product is equal to this right here, but it's also equal to the area of the
Yeah.
parallelogram.
Gotcha.
Hey, it would have been the area of the triangle right here. Oh, here's a triangle. Look. What's the area of that triangle?
Divided by 2.
Let's say divide 2. Area is 4. That area is 4. Cool. Also, hey, what else we got in here? textbook stuff just before we get into 12.5 stuff. Area of triangle. Well, area of triangle, we know we could do that. It's going to be very similar. The only thing is I want to give you points. You know how to get vectors? Vectors from points? Tip minus tail. A couple more things from this section before we get into 12.5. I have another theorem. And I need to put it right underneath of this. Torque. Torque is defined as they use the Greek letter tau for torque, everyone. Tau. The position vector cross the force vector.
Force equals to work into distance, right?
That's right. But that's torque. It's the cross product of a position vector and a force vector. Okay, then what's the magnitude of torque? Well, what would be the magnitude of the torque? I'll put it right above this. Well, if that's the definition of the torque, it's the cross product of the position vector and the force vector, then what would be the magnitude of torque? It would have to equal what? The magnitude of the position vector times the magnitude of the force times the sine of the angle between the position vector and the force vector. So, in this case, might as well take a problem.
Are you going to have to memorize all these formulas, or are you going to give them on the sheet?
You can either memorize them,
Uh-huh.
because sometimes memorization is more how things got developed. You can either memorize them, or if you want, everyone knows PID 3s and 84s, you can store them in the program button. And if you're like, can you show me how to do that? Oh, after class. Probably take less than 2 minutes. Should I do one? You can do a million. Does that sound good? Awesome. If you have questions about that, I'll be glad to share how to do that. Hey, let's do a problem. Everyone, I'm taking this actually as an example. It's on page 838 in your book. Just an example of the book. I can make up different numbers, but I won't. And they got a wrench. They've got a wrench like this. We've got a little wrench thing. There's a little bolt right here. Alright, there's the wrench, there's the bolt. So how long is this? They said that's 0.25 meters long. That's how long that wrench is. Alright, there's the wrench. They stuck a force vector this way. 40 newtons. Anything else? Thank you, they gave us the angle. I mean, this is just going to be a plug and chug problem. They've given us everything. And that's the angle. I do want to point out, everyone, we're going to find the magnitude of the torque. If you're wondering, is there one like this on the practice set? Same thing. Find the magnitude of the torque about the center of the bolt. And that's what we're going to do. Find the magnitude of the torque about the center of the bolt. Alright. No problem. But gosh, we've got the angle, we've got the position vector, we've got the force vector. This is going to be rather simple. This is just going to be a plug and chug. I do want to point out, sometimes students are curious about, like, where is that position vector? I see the wrench right there, everyone. If you're curious, this wrench, the position vector, is actually the vector that would start here and go up this way. That's really the position vector. If anyone wanted to make a note. When you're talking about, but the wrench is going this way, that's the actual position vector. And can I slide that here?
Yep.
So the angle between these vectors, you don't have to do like 180 minus 75 or anything. I didn't want you to think you got to overthink the problem. The theta we're going to use in this math formula is going to be the what? The 75 degrees.
Oh, so the position is also the same direction. So you
That's
have to
right.
change the sign. Okay.
That's exactly it. So I didn't want you to be confused. Think like, do I have to do more with the problem like this? Nope. I am just going to do magnitude of position vector, magnitude of the force vector, and multiply the sine of that angle. And this was what? Just 0.25 meters? The force was 40 newtons. And the sine of 75, we need a calculator. And I'll let you all type it in and we'll just put put a rough answer down. Or I'll just steal the book and see what they wrote.
9.66.
That's what they got. About 9.66. Newton meters. Yep. 9.66 Newton meters. Hey, one more thing before we do 12.5. Maggie, thanks again for bringing this up. Now, when there's a problem in 12.3, it's a neat problem. Somebody might have tried it already and gone, I don't know about this one. It's going to be rather easy now that we've done 12.4. And it says, we won't work it out, but I want us to talk about it. The question is, can you find a unit vector that's orthogonal to I plus j? That's a vector, right, everyone? If you put it in component form, what are the numbers?
1.
1, 1, 0, right, everyone? And then this vector, j plus k. So I'll erase all this. Just make the torque, get out of the way. But there's a question like this earlier, and you might have been like, you might have set up an algebra problem to solve it. But I think right now with cross product, this is going to be rather easy. Can't we just cross these? That's all you got to do. Now they said the word unit though, so when you're done crossing them, do you remember how to make a unit vector?
It's divided by the magnitude.
Right. That was loud too. You know exactly what to do. Hey, if they try to get tricky here and they said, find 2 unit vectors, get your one answer, and what could you do to all the signs?
Make it negative.
Make them all negatives. Switch all the signs. It's just going to stick the vector into what? The opposite direction. So when they play games like that, like find 2, that's what they want you to be thinking of. Just go, I'm just going to go to my answer where the vector's like this, and I'll just put it in the opposite direction. It'll still be orthogonal to the 2 vectors in that plane, right? What do you think of like this desk? It's like, oh, it either goes up, perpendicular, or it's what? It's underneath the plane going down. So if they do a 2 thing.
Ah.
Sometimes they do that. You're going to see they go, find 2, and you're thinking, gosh, I got 1, how do I get the other? That's all you got to do. You know, A cross B versus B cross A. And anything else before we get into 12.5? 12.5 is fun. It's lines and planes. That's the title. There's one more thing. Has anybody looked over the problem set yet? I think I saw some. Oh, awesome. People are already looking at it, or maybe did the textbook problems. You're going to notice this. There's a lot of questions about things like this, where you got to determine. I'm going to give you an example. Oops. They're thinking problems. This is my first example, and that's a dot for dot product. That's a cross for cross product. That's a cross for cross product. And they just ask questions like this. Determine whether or not, first of all, it's defined, let's let A, B, C, and D be vectors. Okay? So I'll ask you this question. This right here, is it a vector? Is the solution a scalar? Or is it just totally, totally meaningless? So it's one of these 3 options. They're either going to give you something that means something like, oh, that's a vector. Has meaning. That's just a scalar value. Well, any scalar value has meaning. Or they're writing something down that's totally what? Meaningless. I got a couple. I think I have 2 or 3 of these in the practice set. The problem set. I should call it a problem set. There's some of these in the textbook. Well, let's do a few of these together. I'll make them up. And we have to do a bunch, but enough to get us thinking. So first of all, if you ever see a dot, what has to be on either side of a dot? I want to point that out. So here's the first rule. If you ever see that dot for dot product, then the opposite side of each has to be a vector. That's the first rule. If you see a cross, what has to be on either side of the cross? Vectors. So let's just start there. So if someone puts a dot down and sticks like a magnitude on one side of the dot, go, wait, that has no meaning. Right? You're either dotting 2 vectors or you're crossing 2 vectors, right? Now, when you cross 2 vectors, there has to be a vector here, do you agree? There has to be a vector here. When you dot 2 vectors, what's the result? Scalar. What happens when you cross two vectors?
Vector.
I love it. And that's probably what we just need to know when we do the problem. So everyone, all right, everything looks good. There's a dot, vector and a vector. There's a cross, there's a vector and vector. Looking good so far. So let's start here. What is all this?
Scalar.
So I'm going to put an S for scalar. So it looks like I got a scalar cross a, what's a vector cross a vector?
Vector.
Can we do that in math? So what is this? Is this right here? Everything I wrote, is this a vector, a scalar, or meaningless?
Meaningless.
This is meaningless. I'm going to put M for meaningless. This is totally meaningless. You can't cross a scalar with a vector. Do you follow me? So these are the questions they ask.
But you can multiply a scalar by a vector.
That's right.
You just can't confuse the symbol.
And I like to do an example, everyone. Do you know what he just said? Here's a vector. He goes, you can multiply a scalar to a vector. Just a vector. You know, I'm not talking about cross products or dot products. He goes, you're allowed in math to multiply a scalar to a vector. I want to give an example. That's a vector, right? But it's not a unit vector. How could we get a unit vector?
Divided by 2.
And that's what you're doing. You're dividing out the magnitude. You're multiplying some number to the vector. What's the magnitude?
Root 5.
Yeah, there you go. See what I'm doing? I'm multiplying this to this. We're allowed to do that. You can multiply scalars to vectors, right? So you can multiply a scalar to a vector. I'll tell you what you can't do, though. You can't take a scalar and divide a vector. That's another weird one. Can you take like a scalar value like 5 and then divide out like a vector like this? No. There's no like divide vectors. Vector, this has no meaning. Look. Just go like this. You can't do that. But you can do what?
Divide a vector.
Yeah, you can take a vector and divide out a what?
Scalar.
A by from all three of the numbers. You follow me? Yeah, that's okay.
That's what we did. Unit vector.
There you go. He goes right there. There's a good example. So let me make another one up. I'll steal one from the book.
Can you divide a vector by another vector?
No. Good question. She goes, can you divide a vector by a vector? Like, I'm going to take vector S.